Wait till 11:31 and then start. Yeah, okay. I think I'll start now. So, good morning, everyone. Uh, you have been attending the summer school and refresher course, I think, for more than a month now. So, you'd be all hopefully not getting too tired of all these talks and activities. But, and it's pretty strange that even after a month, I'm coming in and I want to tell you first, before I get into anything else, is what my understanding of what such a summer school and refresher course is all about. I know there are official reasons for doing these things, but what is the real thing? I mean, what is my motivation for coming and telling you things is a different one. And so let's keep this one thing clear. First of all, this school and for 1.5 months, the intention is not to teach you anything. Now, that is, let me repeat that in this school, you are not expected to learn anything from the school. Now, that is important because you see, so a person like me has spent more than 25 years learning astronomy. And if you all learn astronomy within 1.5 months, that makes insinuation that all of you are much, much, much more smarter than me by two orders of magnitude. And I don't think that's correct. So let's remove that motivation out of the thing that we are going to learn anything from. So then, what is the reason for doing a summer school and refresher course? Exactly, is that the idea is here is that we are supposed to be in an advertisement mode. We'll tell you broadly what is happening, and we'll also tell you the main reason is why do people like me spend 25 years doing this subject, and then you may consider these aspects and then decide for yourself whether you think that this subject is something which you would like to work on, or you may decide that okay, no, I don't think astronomy is the right thing for me. In fact, you may even decide a more fundamental thing, that you may decide that academics is not right for me, because when you have a view of what academics is um, in your earlier, and then you actually what is academics is very different. And for all those people who are teachers and who already are into academics, anything, you may have some idea about what astronomy is all about, what does it do, but then you may realize that this is not my really something which I would be interested in. The hence the primary reason for having such schools, workshops, and giving talks is to help you decide whether you want to do astronomy seriously or not. And either way, if you decide, it'll be the school and workshop will be a success in the whole lot. So, keeping this motivation here, I'm going to give you two lectures. And my first one will be more on motivation. The second one will be what are the questions that we don't know and how are we trying to address it in the future. I do not expect all of you to understand a large number of what I'm saying, but that's not the point, as I was saying. If you can, if my talk helps you to decide, that is will be good enough in the whole. One of the reasons people come to astronomy is because it's an exotic subject. Exotic means something which is rare, And the idea is that we look for systems in the systems which are very much more difficult, and um, uh, things like, and the catchy word around here is something called a black hole systems. Even when I was a kid long ago, the word black holes used to fascinate me, and then I found out that what I had been fascinated by black holes was not actually what what people do really study about black holes. So, or what most people study about black holes. So I thought I'll give you a thing about black holes, and my title is a little strange. It says the Nobel Road to Observing Black Hole Systems, and I'll explain that as it goes, because I'll tell you how why this title is as we go along. So let's start with you already had many classes, but let me start with telling you what is a black hole in my words, in my own words. Now, what you have to do is you have to imagine, and you have to imagine that you take the sun, and everybody knows the sun. You've already had many lectures. The sun is a very big, massive object, and if you happen to squeeze the sun to a size of 1.5 kilometers, the sun is a very big object. Now, just imagine that somehow something happens and the sun gets squeezed to about 1.5 kilometers. By definition, that object which will form, which is called a black hole. So the first message is that black holes are small and dense. A huge sun is put into a region of 1.5 kilometers means that it will be very, very dense, and hence black holes are small and dense. The second thing is, even if you take Newton's law of gravity, that is gm by r square. So we have taken a sun and we have kept m constant and we have reduced r. So what happens is, at the surface of this object, the gravity gm by r square will be very, very higher. So the gravity of black hole can be about this many times that of the Earth. So black holes have powerful gravity. Now, just to explain again, why do they have powerful gravity? The mass of this imaginary object we made by squeezing the sun into 1.5 kilometers is the same. So if the sun became a black hole, the gravity which we would face on Earth is the same. However, if you are going towards the sun, you can approach the sun only to its size, to its r. As you go closer to the sun, the gravity will increase, but it will increase till you reach the surface of the sun. However, if a black hole is so small, you can keep going closer and closer to a black hole. And as you go closer and closer to a black hole, the gravity keeps increasing. And that is why black holes have powerful gravity. That is, they are so compact that regions around them feel a very powerful gravity. So a couple of points. Again, black holes have powerful gravity, and they're small and they're dense. The one important question is that light cannot come out of a black hole. I'll explain that a little bit after this. But let us say that since light cannot come out of a black hole, that means since light is the fastest thing we know, nothing can come out of a black hole. And if nothing can come out of a black hole, no information can come out of a black hole. And if information cannot come out of a black hole, we cannot know what is happening inside a black hole. That is why the surface of a black hole is called an event horizon. Event is something like, I'm giving a talk, it's an event. You can go and tell people that you heard my talk. So, but if this talk happened inside a black hole, you could not have gone and told people outside the black hole that there is an event happened. In fact, in the universe, whatever events happens outside the black hole, because that's the events we can know about or talk about, right? So the surface of a black hole is called the event horizon. Horizon is because something beyond which we can't see, and since we cannot see any event beyond the horizon beyond the surface of a black hole, this surface of black hole is called the event horizon. Now, why can't light come out of a black hole? Because light has energy, and when it comes out, it comes across, it will lose its energy. And let me explain this a little bit uh, further. Let us imagine that there is a person, and let's say I am standing close to a black hole, outside a black hole. Let me be clear. I'm standing outside a black hole somewhere, and let me see if you can see my cursor. But let's hopefully you can. Let's say I'm standing here, and I shine a light, a torch, away from the black hole. So I'm standing outside a black hole, and I'm shining a light away from the black hole. Since I'm standing outside a black hole, this light can escape. It will come out. I know. But when it is going away from a black hole, it has to work against the gravity of the black hole. And working against the gravity of the black hole means that it has to lose energy. For light, losing energy means its wavelength will become longer or its frequency will become lower. In other words, if I was sending a blue light, it will start becoming reddish in color. It goes towards a red color. That is why this is called red shift, going towards red. And in this particular case, this is called gravitational red shift. That is, the light is losing energy because of the gravity of the black hole in the red. Now, so if I am standing here and I send out a blue light to a person far away, the person may see this as a red light. Now, if I go closer to the black hole and do the same experiment again, the light has to work harder. I mean, it has to lose more energy to get out of this potential well. So in that case, what it'll do is it'll lose more energy. So the redshift will be more. It'll become more and more redder. And as we approach and come close to the event horizon, this redshift becomes infinite, which means that no matter what kind of a frequency of light you send, by the time it reaches a distant observer, its frequency will be nearly zero or its wavelength will be very infinite. So in practical purposes, you don't see the light at all. It is in this manner what we say that black holes are black. They cannot emit light. It's not that light comes out and falls back on them. It is this fashion that black holes are like. And this is an aspect which has fascinated people. And black holes are described by Einstein's theory of relativity. And a lot of things happen there near the black holes, and all space time gets curved, and strange things happen. In this talk, this is only all I'm going to tell you about what are black holes. I'm not going to tell you anything more about what are black holes from this one. Because this talk is not about what are black holes. This talk is about something more fundamental than that. And let me start with the history of the thing. Is that black holes are described by Einstein's general relativity. It doesn't matter if you have not really conversant with the general relativity. We'll come to that. But you know, you must have heard of Einstein's general relativity. It's a very complicated subject. And what it was found out by one person who was actually fighting a war in World War One, Carl Schwarzschild, that if you solve Einstein's equations in a particular manner, then you come to a point where you can describe what is called a black hole. It's not sure whether Einstein knew about this, but I mean, he must have known about it, but no one took it very seriously. No, actually, no, they said, fine, this is a nice solution, everything, but no scientist took this concept of, in fact, the word black hole was not formed, and nobody took it extremely seriously at all. You know why? The reason why nobody took it seriously was the first starting sentence of my talk here. I said that you imagine you take the sun and you squeeze it to 1.5 kilometers. How can that ever happen? How can something as big as the sun get squeezed to 1.5 kilometers? This is absolutely impossible. This is sheer imagination, and physics is not interested in imagination. So nobody bothered about it. This is not a question. This is a question of people who are interested in the mathematics of the subject were looking into it, but physicists were not really interested in the question at all. So, and why? Because it seemed that black holes cannot exist. So since the answer to the question, can black holes exist, was practically no, nobody took an interest in this. The whole thing changed when a young man was going from Chennai, those days Madras, to England, and in a ship, he did some calculations which changed the whole idea of this question. The young man was S. Chandrasekhar, and he was very knowledgeable in quantum mechanics and statistical physics. And so what he did was he said that under certain conditions of the stars, when they actually run out of fuel, they start to collapse, and there's nothing to prevent that collapse when the star is big enough. And in such a case, he actually imagined that the system will collapse and form a black hole eventually. There has to be a big enough star to form black holes in the whole thing. For this was in 1940s, and for this momentous discovery, or S. Chandrasekhar got a Nobel Prize in 1983. Note the difference in years. 40 years later, S. Chandrasekhar got a Nobel Prize. Even after that, even after that, this question was not. People were still not interested in black holes. It was not considered something. People thought about it for a while, a little bit here and there, but they kind of till 1970s nobody took much interest, despite all those controversies you hear about uh, uh, Eddington and Chandrasekhar. Not the large number of scientists were not bothered about this uh, black hole things. The reason was nobody knew for the answer to the second question. See, there's a very big difference between can something exist and do they exist. Chandrasekhar has shown a way, and Eddington had also argued that possibly that nature may find a way to stop this thing from happening, and he could have been right. There was nothing to, but we were not sure that they really exist. And if it just exists in terms of possibility, then it is not a reality in the whole thing. For example, I keep you example. There's a lot of things which are very much possible. Like you could have uh, 300-storied buildings in India, or you could have a building in the world which is 500-story buildings. In fact, a civil engineer can actually design it and tell you that this is possible. But the question is, it doesn't exist. Since it does not exist, why bother about it? So the question which was bothering people, or would have prompted people to start working or thinking about black holes, is do they exist? Of course, the answer to this question is yes, and that is why I'm giving you this talk. But from now on, I will not give you a talk, but I will try to be more um, like a lawyer, and you will be like judge, or more precisely a jury, and I'll start giving you evidences. Why do we know that the answer to this question, do black holes exist, is yes? And uh, how many years it took us with all of evidence to now be confirmed that black holes exist, and how did this whole happen? So it's more like a legal case or more like a history case. So let's start beginning. Now, when you want to answer a question like can black holes exist, this one, then like Chandrasekhar, you can go with a pencil and paper and solve equations. But if you want to ask a question like do black holes exist, you can't do it with pencil paper. You actually have to go look for them. And since you cannot look for, there are obviously no black holes in the Earth, you have to look for them outside. So you have to look at the skies and all. So this is an image of long time ago, 1970s image of the sky. Now, why does it look like this? So you know the sky is like a dome on top of us, but when we want to put it in a two-dimensional piece of paper, we represent like this. Just like the Earth maps are put in this kind of a shape. This is called Maclaurin shape. So this is like the sky, the whole sky, and put in a map form. This is not the image which anybody would see from anywhere in the Earth at any time, because this is an image made of X-rays. And even if our eyes could see X-rays, we would not be able to see this because thankfully the Earth's atmosphere absorbs X-rays. And because the Earth's atmosphere absorbs X-rays, you cannot see them from Earth. The only way to see X-rays coming from space is that if you go to space, and hence this subject started in 1970s, late 60s, when satellites were set up. So only when technology was there for satellites to come up did the question of uh, this hunt for black holes started. And so these are X-ray sources in the sky in the whole thing. Just for example, for this discovery of uh, finding X-ray sources in space, the 2002 Nobel Prize was given to Riccardo Giovanni for his pioneer discovery of cosmic X-ray sources, because that became so important in the whole thing. Again, let me tell you a time scale here. The discoveries were made in 65, 67. The Nobel Prize was given in 2002. Okay, let me come back to this. Now, along this line, this map is drawn such that along this line is our own galaxy called Milky Way. By now, you may have heard a lot about the Milky Way and all, but I do hope that you know what this is. That when you look up in the sky, you see a band of stars in the sky. If you have not seen this, you should go and see this at some time. Go to a nice dark spot and see the Milky Way. I mean, irrespective of your all your interest in astronomy or whether you are interested in science at all, I know there are some people who have not seen the Milky Way, and that's a big shame. That is like some people living through their life and not seeing the moon. Uh, you must see the Milky Way to appreciate our nature. That aside, when you see this band of stars in the sky, this band of stars belongs to our galaxy. Our galaxy consists of a large number of stars, and what this map does is it aligns the Milky Way along this line. And in what you find is you see these points here, sources, point sources. These sources are within our own galaxies, and these sources we've just deemed them X-ray binaries. Okay, so just remember that there are sources within our own galaxy, X-ray sources, and we call these things X-ray binaries. The energy output of these X-ray binaries, that is the luminosity, that is how much energy per second they come out, is about 10,000 times that of the sun. They're very bright. They're very powerful sources. However, that's okay. It could be a very big star. If it's a big star, it could give out that kind of energies. The the sun is an ordinary star. This could be exotic, very big stars which are giving out a large amount of energies. However, they are variable in milliseconds. Now, variable. What does variable mean? They flicker. It's like you take a candle and there's a small breeze blowing. The candlelight will keep going. Candle will keep moving up and down. It flickers. The candle will flicker if there is a small breeze. What does flickering mean? That suddenly the intensity of the candle will go down by a factor of 2, 3, and then come up again. So it becomes half bright and full bright and half bright and full bright. And what time scale does this occur? This will occur in time scales of seconds. For 1 second it is bright, 1 second is off, and not regularly or sometimes regularly, but it's a variation on time scales of seconds. Now, if I ask you that the sun will disappear, if I tell you that the sun will disappear in 1 second, you will know that that's not possible. Or the sun will suddenly become fainter by a factor of 2 in 1 second, you know that is not possible. Why is it not possible? Because sun is a big object. However, a candle, if you blow on it, within 1 second it will go off. This is a common sense understanding that small objects can very fast, big objects cannot very fast. And this common sense statement we can put into rigorous science statement because we know that the speed of light is the maximum. So we can make a statement that a system can vary on a time scale delta t only if its size is less than the distance traveled by light in that delta t. So for example, if you take a system which is, can a system vary in 1 second? For it to vary in 1 second, it must be smaller than the distance traveled by light in 1 second, which is 300,000 kilometers. So, what this physics statement is telling you is that a candle is smaller than 300,000 kilometers and the sun is larger than 300,000 kilometers, which is not very profound. However, let's come to this X-ray binary strings. X-ray binaries are variable not in seconds but in 1 millisecond. Now, light travels 300 kilometers in 1 millisecond. So, what does this mean? This means that the size must be less than 300 kilometers, yet the total energy coming out of these objects is 10,000 times that of the sun. So can you imagine? Just think. One has to imagine these things. That you have a size which is so small, about as small as a district in India, and but it's giving out 10,000 times more luminosity than the sun. Before we get to that, let's go to something else. Let's go to something else. Apart from these sources which are in our own galaxy, there are sources outside the galaxy, and this you may have heard today in the morning by Gulab. These sources are active galactic nuclei. Just to repeat, just like a galaxy, there are billions and billions of other galaxies. Some of these galaxies, only a fraction of them, have a bright center. So the center of those galaxies are extremely bright. Those galaxies which have a very bright center are called active galactic nuclei. And they also give out X-rays and optical and lots of energy. They're very bright in the center. Only few of them are very bright. The thing about these active nuclei is that the energy that is coming out of the center is 10 times that of the whole galaxy. A galaxy comprises of 10 to the power of 11 stars. That is 10,000 billion stars. And the small point center in the center of the galaxy, this AGN, activity nuclei, is 10 times brighter than a galaxy. So, in other words, it's a million billion times brighter than the sun. A million billion times brighter than the sun. Yet, it varies in minutes. And you know that light takes about 8 minutes to come from the Earth to Sun. So this object must be much smaller than the distance between Earth and Sun. However, its the amount of energy it's giving out is 10,000 billion times or million billion times more than the Sun's luminosity. What kind of objects can these be in the whole thing? How do you produce energies for this kind of system? You can do it with nuclear burning. Nuclear burning is a way by which stars shine. We have already known that two hydrogen atoms combine to form helium, and then that's how you get the sun produces energy. And you may have also learned in school this formula of how when you combine the two hydrogen atoms, the amount of energy by Einstein's equation is delta E point zero. So if you, otherwise, if you take 1 gram of hydrogen, merge them together, you get this many ergs of energy, which is quite large. And stars shine by hydrogen bombs explode by very powerful systems. However, this is by far not the most powerful system in the universe. The most powerful system in the universe is much more simpler. It is just gravity. We also produce energy through hydroelectric power, that is water falling down that produces energy. So if you put things in a potential in a gravitational field and let it fall, you can create kinetic energy. And this is a powerful source of energy for if a meteorite hits the Earth, it is not the meteorite which is coming at a high velocity. Much of the velocity comes when it is putting into the Earth. If a meteorite goes and hits instead of Earth something like Jupiter, it'll have a much higher velocity when it enters Jupiter, because Jupiter has a stronger gravity. So it'll happen for the Sun. It'll have a much stronger gravity. But let's imagine what will happen if you throw a stone onto a black hole. By the time the black stone goes close to a black hole, its speed is so high that its kinetic energy is so high, it is about 10 times the rest mass of its particle. So in that sense, it can produce 9 and 10 to the power 19 ergs per gram. So strong gravity is the most powerful source of the energy in the universe. So now let me, as a lawyer, put these two things together. There are objects in the sky, X-ray binaries and agents, which are very powerful and very small. I know that strong gravity, which can be in terms of black holes, are very small. Black holes are very small, and they have the potential to have powerful sources of energy. Hence, I will like to combine them together and say these objects are black holes. This kind of reasoning is good in science, but not good in legal things. This is called. This is not exactly uh, the right. This is called some kind of circumstantial evidence, not true connection between things. But it is a powerful argument in any case to suggest that these things are actually black holes and pulsars. So I've just said that. So does this mean that there's a black hole in there? So before we get it, let me. I'll talk about this much more tomorrow. But let's talk. How does a black hole produce energy? The idea is you have a black hole in the center. You have a star, regular star like the sun. The star is going round the black hole. Matter from the star falls towards the black hole, but it can't fall directly because it has an angular momentum. And this angular momentum, what it does is it makes a ring-like object, and because of the viscosity, it starts becoming an accretion disk, a disk-like object. So, okay, let me repeat again. Matter from the because the black hole and the star are close by to each other, matter from the star will fall towards the black hole. It has angular momentum, so it will form a ring. Because this gas has viscosity, this ring will not remain just like the Saturn's rings, but instead will start diffusing out and go towards the black hole. Viscosity also produces heat, so this disk or this disk-like thing will become hot and it become very hot close to the black hole. And when it becomes very hot close to the black hole, it gives out a lot of energy. So it's the disk which is giving out energy. Black holes are of course black; they don't give energy. This one, I will talk a lot about this in the next talk, but there is one big problem with this. This is a painting, and in a legal court case, you cannot show a painting. That's not evidence. This is what we're seeing is our imagination, and we can imagine a lot of things. How do we know that this is really happening out there? How do we know this is how emission produced? So from now on, I promise you, I will not show you any more paintings. Anything which I show from now on is going to be a real image. So before that, these sources are very far away, point-like sources. We can now, if the black hole, just one important point is, suppose it's only the disk matter going round a black hole which emits light. Black hole cannot emit light by itself, right? So if a black hole is, if this star was not there, if it's not there, then this black hole will not emit light. It'll just be a black hole. Can we really find out whether these isolated strong black holes are there or not? We can, and here is a very old image, now more than 30 years old. No, not 30. Yeah, around 30 years old, from Hubble Space Telescope, which, as you may have known, that is one of the world's finest telescopes in the world. It cost at that time $1 billion, and this is one of the most famous photographs it has ever taken. It is of a galaxy far, far away. And when you looked at the center of the galaxy, far, far away, it saw a ring-like matter. Now, this is not accretion disk. This ring is actually not close to a black hole. This is a ring far away from the black hole. And when it saw this ring, it could find that this ring is actually rotating. It's revolving around the central object. And because it's revolving, they can do that by looking at the line emissions from this ring. And they can measure the speed. And from the measuring the speed, they can infer that must be a very heavy object here in the center. And that could be the evidence for a black hole. I'm sure you may be disappointed. You may not be convinced by this image, at least, unless you analyze it carefully, that what I'm saying is correct or not. That's not. However, let's take a look at this in a why and why is this bad? That is because this is a galaxy very far away, and we can barely see it, and that is what is causing the problem. Why can't we do a better experiment and see our own galaxy center? maybe there's a black hole sitting in our own galaxy center. That's what people thought. And as you may know, the answer is that there is. Uh, Maybe we should look at our own galaxy center and see what we get. There are two problems with looking at a galaxy center. First problem is that you may have already realized that hearing my lectures that the universe is a dirty place. It is indeed very dirty. The universe has a lot of dust all around it, and whenever something is dust, you can't see through it. If you have gone to dusty roads, you'll know that. But that is not a major problem. We can use infrared and all to actually look through dust and see through things properly. That's not a serious sample, but problem. The second problem in all astronomy is that stars twinkle. Now, why do stars twinkle? Stars twinkle because when the starlight enters the Earth's atmosphere, which is not still, it gets diffracted, and its wavefront keeps changing. So when you're looking at the star will be moving a little bit here and there in your actual image, and that movement of the star moves because the wavefront is continuously changing. The air on the atmosphere is constantly changing. That's why it gets refracted, and you see different positions. And when that happens, excuse me, you infer this thing as a twinkling. When you actually take an image of that star in a detector, you get a big blob, not a point source. And that's because the Earth's atmosphere is twinkling it up. How do you prevent this? You go to space, like Hubble Space Telescope. You go to space where there is no atmosphere and then you can get sharp images. But if you do that, you are limited by the size of telescope. The Hubble Space Telescope is a 2-meter telescope. The new James Webb Space Telescope is a 6-meter telescope. These are small telescopes. In Earth, we have 10 meters, and now we are looking at something like having 30-meter telescopes. 10-meter telescopes is about 4 times or 5 times more powerful than the 6 meters, and 10-meter telescopes are more than 100 times, more than 25 times more powerful than 2-meter telescopes. Sorry. So if you go to space, you don't have an atmosphere. On the other hand, your telescopes are small. So how do you circum this wall? People found an ingenious way to do this, and you will have heard about this, so I will not go more. It's called additive optics. The essential idea is the starlight is getting distorted because of the atmosphere. So what you do is you send a laser light like this thing. The laser light goes through the star's atmosphere and comes back. From the way the laser light has deformed, you get to know what this turbulent atmospheric layers are doing. And based on that, you correct your mirror or the mirror in such a fashion that compensates for what the atmosphere is doing. And all this is done in 1 millisecond, and the mirrors are moved in nanometers. This is the most sophisticated technology ever done on a feedback loop system in any electronic or mechanical system. It took a long time, and you probably have more talks on this in the summer school. It took an absolutely long time to get this into function, about 15-20 years of research, and finally they got it. So they took the largest telescope, 10-meter telescope, and tried to look at what happens if I look into the center of our galaxy, right? After many years. This is what I saw in 1992. This is 1992. The red cross is didn't see a red cross. This red cross is put as a marker to show the center of our galaxy. What I saw was nothing. The center of our galaxy is a boring place. It has 1, 2, 3, 4, 5 stars they saw. And these stars are very common, regular garden variety stars, which you find everywhere. Nothing special about these stars at all in the whole thing. So after doing all this adaptive optics, using your largest possible telescope, spending 15 years of research, the answer you got was nothing. So science can be often be disappointing. However, science has a redeeming factor that often what you find nothing is actually not nothing. So you have to persist. So what people did was they took photograph again and again of the Milky Way. like this. I've told you that I am not going to show you anything which is not real. All this is here is that photographs taken at different dates of the Milky Way, and this is long ago. Now we have many more photographs, but I'm showing you sometime till about 20, 30 years ago. I mean, till 15 years ago. What did they see? They saw that the stars are moving. This is not that amazing. We can see stars move. Stars actually move. Stars are moving. The interesting thing about the stars are not moving randomly. They have a pattern. And interesting one is this one. This object is not there, comes back and goes up. But the most important star is this star, which I which goes and follows this shape. It's called S2. Right? If we had shown this image to a person 300 years ago called Kepler, he would have recognized them immediately because the laws of how these objects move are named after him. Kepler, what he did was he found the ways by which planets move around the sun. Here, we have a similar system, but we have stars moving around something else, and there's nothing here. In IUCAA, there's a program by which school children, class 8, 9 students, sometimes come for a week or two and to see how scientists function and everything. And one of the projects we give them is that you take this star, we tell them how long it has taken to go from here to there, how big this distance is, and ask them to find from their knowledge of general physics of the Kepler, what is the mass of this object here. And they correctly find the mass of the object to be 2 million times the mass of the sun. So there's an object sitting here which is 2 million times mass of the sun, which can't be seen in at least in infrared and optical, and very, very low. So this proves that there is a black hole in the Earth. For this, the 2020 Nobel Prize was given to uh, Renard Genzel and Andre Ghez for discovery of a supermassive compact object in the center of a galaxy. People were very upset that they didn't say black hole. They still were being careful in Nobel Prize team and said a supermassive compact object at the center of a galaxy. And for that discovery of the stars going round the black hole was given by tourist Nobel Prize winner. But why did they say supermassive compact object? Because see, evidence is, of course, what they saw was something close and compact. And let me bring out to you. The black hole in this image is still very, very tiny. This star does not get eaten up by the black hole because it is still far away from the black hole. It is very far away from the black hole in terms of it. This black hole is a very small thing there. So one wonders whether one could actually see and in what people do. Can you actually photograph a black hole? Can you see what a black hole is like? Okay, so to image a black hole, you would need a camera which has a angular resolution of 0.1 milliarcsecond. Let me remind you or tell you what angular resolution is. Angular resolution is a property of a camera to distinguish two objects which are slightly away. So if they are separated by a certain angle, and this camera can say yes, there are two objects. If they are very close to each other, a camera will say there's only one object. If they're slightly separated away, it can say that there are two objects now. So that is called the angular resolution of a camera. What you need is an angular resolution of a camera which is 0.1 milliarcsecond. Now let me remind you what a 0.1 milliarcsecond is. A full circle is 360 degrees. You divide a full circle by 360, you get 1 degree. You divide a degree by 60, you get an arc minute. You divide an arc minute again by 60, you get an arc second. You divide an arc second by 1000, you get a milli arc second. And then you finally divide that milli arc second by another factor of 10, you get 0.1 milli arc second. And this kind of a angular resolution was required. For that, you needed, and angular resolution improves with the size of the camera. The larger and larger camera you have, the better angular resolution you can get. In fact, there's a law that you, depending on the size of the camera, you cannot get better angular resolution than uh, for a given size of a camera. The angular resolution is fixed. You can't get better than that. Of course, it will always be worse because the camera is not perfect, but it can never be better than that. So people use the world's largest telescope, I mean size wise, on Earth, and that is the Earth itself. They put two radio telescopes on opposite sides of Earth and measured the things together and did a complex interferometry studies to find that you can actually image the black hole. And here I will show you one of the images of the black hole, and look at its units first, micro arc seconds. This is a simulated image, but the Event Horizon Telescope got this image out of a black hole near the a neighboring galaxy M82X1, M82, and this black patch you see here, that is called a black hole shadow. And this black hole shadow comes because light from behind cannot penetrate to it. It gets bent in various ways, and that is why. And all general electricity light bending effects happens close, and we can observe this now, and so we can now image a black hole. I'm sorry about uh, just about a few weeks ago, the people there also announced the collaboration event horizon also announced a similar photograph of the center of our own galaxy, Milky Way. This is the center of a nearby galaxy. They also have announced and shown an image of a. I just forgot to put it up here, of a own galaxy's image. So now we can actually see the black hole in the event, and this was done this year and last year. So in another of 10, 20 years, we expect to get they may expect to get a Nobel Prize for this, because this is now clear evidence that there's black hole. Of course, there's no doubt of now black holes existing, because we got we now have detected gravitational waves, which you would have heard about now, so I won't talk about as much. That is when two black holes merge far away, they give out this tiny rippling in space-time. This tiny rippling of space-time is going to be this very sensitive detectors, and this is one of the first detection of two black holes merging, and the signal is identical to what was predicted for two black holes merging, and hence we now show that gravitational waves are there, and which also proves that there were black holes. In 2017, the Nobel Prize in Physics was given for gravitational wave detection, and hence now we are completely assured that there are black holes in the universe. So what next? Lots of things next. Although now we know that there are black holes in the universe, we know nothing about them. Let me start with one thing. I told you that this black holes flicker. The change in X-ray binaries were changing in milliseconds. Why do they do that? What is the periodic way in which these things vary? Can we actually test Einstein's theory of general relativity by this variability? Do all space-time gets curved here and all? Can we actually measure that curvature of the space-time? How do this form? What is the process? We have no idea of these questions. And my next class I'll go into more details about what are the things we don't know. But let me infer. You see this blue little things here? This blue thing which is going up and down. It's called a jet. One of the problems I had when I was in school was I was taught very badly, and all of you must have been, a subject called biology. Biology is a wonderfully interesting subject, but many of people, I think, do not teach it very well, and hence people like me went into physics instead of doing biology. Uh, and the reason why we didn't like, at least I didn't like biology, was you just name things. You say this is a flower, this thing, you don't explain what it is. Later, I realized that much of the new things in astronomy is like that, and jet is one of the things. We just name it, jet. What is it made of? We don't know. We have been seeing this jets for last uh, 20, 30 years. Is it made of protons and electrons, or is it made of normal matter? We don't know. Is it just sheer energy coming out? We don't know. How is it produced? Is it produced? It can't be produced inside a black hole. So how is it produced? We don't know. Is it produced by the spin of the black hole or because of the rotation of the disk around it? We have no idea. How do we see a jet? What kind of particles are produced inside these things? We have very little idea on all this. We have speculations. We have theories and speculations, but nobody has been able to prove anything of that. So there is a large number of questions to be answered and to figure out mysteries. And to do that, we have a large number of Xray space observatories right now. Most important of them being, as far as is AstroSat here. AstroSat has been doing a wonderful job in looking at these black hole systems, finding out how they vary in time, how they're doing, and all these. If you get into all these data analysis and are unraveling all these satellites and big times, are unraveling how black holes systems work, and we hopefully we'll try to understand them better. And as we look at them more and more mysteries unfold, and so our continuing space of going through, and we hope to, and I know that as we go along, the questions which will be asked will be more, and as these questions get answered, we will get there'll be more and more Nobel prizes which will be shared from all of us on the subject. And so I'll stop here and leave you with this image and see if any of you have any questions at this stage. Thank you for listening. I'll have to stop sharing to see, or maybe I can just do an escape. I don't know what happened. Yeah. All right. Where did the Zoom go? Okay, let me see if I can get a chat. Okay, let me see if I can answer some of the questions in the chat. I'm sorry, I didn't hear that. So sorry. Uh, let me. Sneha Singh is just had a question to me at around asking me what does the red cross indicate. Let me increase the volume if people can't hear me properly. Okay. What is the red cross? The red cross was put by hand. It is where we expect the center of a galaxy to be, and because in that point there is the black hole, that is where the stars are moving very rapidly in the system. So hopefully Sneha, that was the answer. uh what are the, let me like okay, Sneha says fine, but let me go back. What are the key differences in terms of obtaining data between a square kilometer array and the James Webb Space Telescope? Oh, completely different. I mean, the square kilometer array is a ground-based telescope. It will work on radio frequencies. James Webb Telescope is an infrared and telescope. It's a infrared telescope in space. So obtaining data, I mean, this is the difference between the two. Their science goals are completely different, and they'll be looking at things quite differently. Is that okay, Tanishq? Uh, that See, one is a ground-based array of telescopes. The other is a single telescope in a space, largely. One looks at radio frequencies, another looks at infrared. Okay, let me go to Vinasha Kalwani. In this image, a black hole looks like a 2D disk. What is the shape of a black hole? The black hole is actually, if a black hole is not rotating, it's a sphere. It looks like a 2D disk because we are looking in and whenever you look at a sphere, it looks like a 2D disk, right? Like a circle. And that is why it is that. So black hole is a sphere, but when you take a photograph of a ball or thing, it looks like a circle. And that is what it is. And that's called a black hole shadow in the system. Okay, let me go slowly. Sorry. Can you please clear me about the surface of the black hole and event horizon? They're the same things. The event horizon is the surface of the black hole. It's just a thing. Can you talk about rose globe in some points? A rose globe, let me just show that if you can still see. Rose globe is a technical term, I mean, it's a classical term where uh, these are two gravitating objects. If you put a particle here, the particle will go here. Put a particle here, the particle will go there. There is a in between point there where the particle will be in equilibrium. That is, it can either go here if you push it this way, if you either go here. Then you draw equipotential surfaces in gravity along these two stars, and those are called rho slopes. So rho slopes are mathematical terms to construct how will matter flow from this star to the other star. Tanishq wants to know that can SK obtain accurate data black hole more than JWST? Tanishq, this is not a race. I mean, nobody's going. I mean, both of them will do their own things, and we combine together to find things. It is not that one will do more accurate. It is like saying that you're going to look at an object from different views and sides. So you will understand nature of. I mean, whenever, even when we look at cosmology, when we look at everything adds to a science potential to come to a story. It is not that, for example, don't get me. Okay, suppose I showed you that image of a black hole, right? The first question you can ask is how did it know to look there? It took a lot of other observation science to find out where to look for, because what is the actual where is the center of a galaxy? So there are a lot of all these satellites and all will not do anything better or worse. They'll combine together to do what's them. There's no. I don't. She can ask once a color gradient in the actual image of a black hole. No, it's a one color image. It's just that it shows intensity. So it's just a. You should take it like a black and white image. Actually, it's just been made color correctly. Right? There is no color in that information. It's a black and white image. No. The Vinasha Kalvani asks whether captures the shows one accretion disk. It does not show the accretion disk. Those objects which this. Let me see if I can get back here. This is not an accretion disk. See, if there was accretion disk, they couldn't have done this. Then it would have been a very bright X-ray AGN like object. This is the black hole which is quiet. But why does it shine a little bit? There's some amount of gas falling on it. Probably spherical or something. Not like the huge amount of gas falling in accretion disk. So it's something like you have a black hole and there's a collection of gas around it which is glowing spherically. And that is why it looks like this in the whole thing. This one is more brighter than that one because the black hole is spinning and it wraps space-time in one thing. And you see two cross images. That is because of the light bending effects in the whole issues there. All right. Let me go a little further. How do I go further? Wait. Hmm? Maybe I should. Where did chat go? Chat. Just a second. Chat. Okay. What stops black holes to collapse even further? I'm not sure I understand. Black holes are collapsed objects. So what is happening inside a black hole, we don't know. Whether it's collapsing inside and is totally irrelevant. What happens inside a black hole, we can never know. So the surface of a black hole remains the same because it is the point from which no light can escape. It's not a surface. It's not a solid surface. It's a point from which black holes from which light cannot escape. That remains the same. And if you, as you put more matter on it, the point from which black hole light cannot escape keeps increasing. So the size of a black hole keeps increasing as well in the whole thing. Do black holes have poles? No, black holes don't have cannot have magnetic field. They cannot have magnetic field because magnetic field means that there's, like, for example, the Earth has a magnetic field. That is because the currents inside the Earth, but and which can be known by a person outside who is seeing the magnetic field. Since nothing can be known from outside, black holes do not have magnetic field and hence don't have poles. Should we see the curved filament-like structure in place of diffuse light? Should we see the curved filament-like structure in place of the diffuse light we've seen? No. I mean, I interpret the question. Is this what we expect to see? Yes. Um, you expect to see this because of the black hole is spinning, we know, and there is the light is not uniform surrounding this black hole, and because of these complexities, we do expect to see different kind of structure like this, like an image like this.
Can I just hello, Subrat here. I was
Yes,
just
yes, but
yeah. I had seen somewhere in some in other images. Maybe it was more resolved. In place of this diffused light structure, there were this curved hair-like structure in that region. Or did I?
no, those are simulations.
Oh, those are similar. Okay, okay,
Simulations. This is a real thing. I'm
okay,
not showing you any simulation.
okay, 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 okay.
Those are the kind of funny things you see in that movie. Which movie was it? And that things. But those are simulations.
Okay. All right, all right, okay.
Vinisha, is there a chance for human being to survive falling into a black hole? How do I care? You fall into a black hole, you will not be seen again, right? Because nothing you can't come out of a black hole then. So once you fall in, person outside will never know. But if you're asking for yourself, that depends on the size of the black hole. If the black hole is very, very large, the tidal forces in the black hole will be not big enough. But if the black hole is small, the tidal forces will rip you apart and will kill you. But if the black hole is very large, you can go in, but it doesn't matter. You will not be able to tell anybody what happened after that in the whole thing. All right. Is that the end of my talk? No.
Sir, I have a question. Can I ask?
Sure. Okay. Yes, please.
So, there are some contradictory theory to the existence of true black hole. Like, I would like to mention a theory gives by Dr. Avas Mitra, like true black hole does not exist. What we observed as a black hole, that is actually eternally collapsed.
Hmm.
And he also says that theoretically the black hole's mass should be zero. But we have find black holes with finite masses. So is it better to say it quasi black hole? Later on this theory, Daryl Litter and Stanley Robertson
Okay,
also gives the
okay, okay,
same
okay,
theory.
okay. Then let me interrupt. There are lots of people with
How do you look?
lots of theories, right? Everybody has their own theories and everything. But what science we do it is more or less by democracy. If 99.9% of scientists believe in something, that's what becomes reality. Later, that 0.1% may happen. You may convert people by showing more data and more material things. But right now, uh, a vast majority of the uh, scientists do not agree with Abbas. Vast majority. I mean, in fact, nobody else apart from Abbas. I mean, nobody. Lot of people. So in that sense, there always be people who are writing something controversial. There's hundreds of them. Not only in every field in science, there are always people writing something different. But what we do is we take the general view, the consensus view. If only about 50% of people believe in this and 50% do not believe, then we say that this is contentious. We don't know for sure. But by the time 98, 99% of people believe that this is was true, we say that that is science. Did I answer your question? Yes.
Okay, so thank you, sir.
Okay. I don't see any more chats. Some. Let me see if I can.
Sir, am I audible, sir? Um, uh,
Sorry. I'm not. Let me bring it back. Yes. Somebody else was asking a question.
yeah, yes, sir. Sir, so basically I was asking that you said that there is a jet from the center of the black hole. So why we are not getting any clue of this in the real picture, sir? So if we are looking from the top, there should be something like this at the center.
I'm extremely sorry, Chetan. I couldn't understand your uh, words. If you can write down in the chat, it will be better.
Yeah, okay, sir.
Okay. While Chetan writes down the question in the chat, is there anybody else who wants to ask a question? Okay. All right. So then we can perhaps. Oh, it's already 12:35, and everybody has to go for lunch, and we'll come back again for this thing. So, Chetan, there's something called that Google Documents, right? You can write your questions there, I guess, and I'll be able to access that in that place.
Yes, sir. Okay.
Okay. All right.
Okay, sir. Thanks.
Okay. Thanks. If I don't think if anybody else has any more questions, and we'll meet again tomorrow, and where we will discuss more serious things about what are the questions which are still uh, lurking, and we have to answer them, and which we'll need to answer in the next 20, 20, 30 years. Right? Okay. Bye, everyone.
Thank you, Ranjeev. Bye.
You are there, Debrati? Okay. All right. Bye.